Okay, this is 9.3, Gibbs free energy and thermodynamic favorability. So this is going to be kind of a long one, although some of it's going to be review and some of it's going to be new. Spontaneous, also known as thermodynamically favored processes. So you'll see a lot of TFs because I want to try to avoid using spontaneous because that's easily misinterpreted throughout science. These occur without outside intervention. Fast or slow, doesn't talk about rate at all. Just because it can happen, it could be super slow, could be super fast. As you know, most combustion is fast, graphite to diamond, super slow, although both occur on their own. So we have this idea of kinetics and thermodynamics. Thermodynamics will tell us, will it occur at the given conditions? If it does, spontaneous, there's the TFs, thermodynamically favorable. If it won't, not spontaneous or non. Kinetics tell us the speed of the reaction. That's all unit 5, okay? So we're not going to be looking at that much. However, on the AP test, it might be a little blended together. So what determines this? This is looking at chemical potential energy of the system before the reaction and after. Less potential after means that it's going to be thermodynamically favorable. This is our Gibbs free energy, the change, negative, spontaneous, positive, not spontaneous. I can't say this enough. Spontaneity doesn't mean fast or slow. Totally different. Now, reversibility. Anything that happens spontaneously, meaning thermodynamically favorable, is irreversible. There's a net release of energy to the surroundings, so it can't go back without outside intervention. So it can't go back unless you added electricity, added heat, all that kind of stuff to make it go backwards. Something that's reversible, like equilibrium, there is no net change in free energy. So because there's no net change, then it's going to be a reversible process. If a process is thermodynamically favorable in one direction, it must not be spontaneous or thermodynamically favorable in the opposite direction. And that kind of makes sense, right? The idea is that when we think of anything delta H, delta S, if it's positive one way, it's got to be negative the other way. That's the way chemistry works. So it's thermodynamically favorable. This awesome car is going to break down and get all rusty because it breaks into more parts, gases, particles, all that things down. However, if you were to go the other way, it's got to be not thermodynamically favorable. We have to consider endothermic, exothermic considerations. So thermodynamically favorable occur because they release energy from the system. Now, most are exothermic. Some are endothermic. However, you have to think, how can something absorb potential energy yet have a net release of energy? And that comes from the idea of entropy. So let's take a look at just a simple concept dealing with entropy, and not in a chemical sense, but in a physical sense. When a solid melts, the particles have more freedom of movement. So going from a solid to a liquid, this is going to be an increase in entropy. More freedom, more randomness. More random, energy is released. Of course, we've already talked about this as entropy. More microstates, better phrase than more random, but as long as you're not saying less ordered, I think that's the one you really want to avoid. Melting is an endothermic process, so you have to add energy, yet ice will spontaneously melt above 0 degrees Celsius. So even though it's endothermic, meaning lending towards not melting, the increase in entropy overcomes this problem, causing the reaction to end up spontaneous. So endothermic can happen, it's just less likely to occur. So enthalpy and entropy, these two factors determine spontaneity. Enthalpy change, entropy change. Enthalpy change, your delta H, as we've known from before. Quick review, generally measured kilojoules per mole, careful of the units. When we have stronger bonds, we have more stable molecules. And a reaction generally exothermic if the bonds in the products are stronger than the bonds in the reactants. Exothermic, energy released, delta H is negative. So just recall those. Endothermic, energy absorbed, delta H is positive. Enthalpy change favorable for exo, unfavorable for endo, but that doesn't mean it can't occur. It's just not as likely. Entropy change, difference in randomness, number of microstate arrangements in a possible system. Ooh, I don't like that. Not disorder. More randomness means that there's more ways to arrange the particles, more microstate arrangements. I try to avoid order as much as I can. Now, entropy contribution. You might remember permutations in math, number of unique combinations. You might think of flipping coins. Similar idea. Now think about an ice cube versus the gas particles. Those gas particles can arrange themselves way more combinations in a 3D space than the solids could in their little cube. That's, again, gases are going to have more entropy than solids. Algebraic signs, because you're going to see this concept comes up in a lot of different multitudes. Positive delta S, we have an increase. Negative, a decrease. Again, entropy change is favorable for an increase, unfavorable for a decrease. So these different combinations of enthalpy and entropy being positive and negative, we have all these different combinations, which we're going to kind of summarize on the next few slides. Now, there will be math with this. Later, we'll think about that and calculate those. However, when we think of this, we'll be able to see enthalpy driven. The enthalpy makes it spontaneous. Entropy driven, the entropy changes it to make it spontaneous. Both, to where now both of them will drive it to be spontaneous. That means it's delta G is very low, or negative, I should say. And neither to where it cannot occur because both are unfavorable. Now, what this looks like from a sign standpoint, delta H negative, very good. Delta S positive, good. Both of them combined will definitely make it spontaneous under all conditions. Both of them, one positive, one negative, will mean that it cannot occur at any condition. Now, this all relates to what's called Gibbs free energy. Max amount of work energy be released to the surroundings, constant temperature and pressure. Often called chemical potential, similar to storing energy in a mechanical system. So it can be shown that the change in entropy times the temperature of the universe is the enthalpy of the system minus the temperature times the change in entropy of the system. This turns in more commonly to Gibbs free energy. Now, a little side note, often we'll show Gibbs energy equation without the little degree sign because it's a pain. I've done it. You'll see it in books. You'll see it in lectures, especially even on like AP. It means standard conditions. Pure substances, 1 molar solution, 1 atmosphere. Those are standard conditions. There will be later calcs that are not standard conditions. AP may not tell you any difference, but you need to recognize that it's not at 1 molar and it's not at 1 atmosphere. Or some contaminated substance, but I don't think that's as obvious. Can be devilish, but they're usually pretty obvious, okay? They even might have something like a normal one, and then they would say, changing the conditions, what would this be now different? So the idea is that they've really made it clear that, hey, this is now no longer at standard conditions. But the general format, you got your delta G is equal to delta H minus T delta S. You probably remember these from honors camp. So delta S of the universe determines if a process is spontaneous. Delta G also determines it. Delta S of the universe is positive when spontaneous, so delta G is negative. So when something is positive in the universe, that means we're going to have a negative value here. So when it's negative, we got spontaneity. Now, some mental math, because there'll be some parts to where you're going to be calculating these for sure, and then other parts where you kind of have to understand, based upon the conditions, what does that mean for delta G? One, this saves you time on the AP test, but also there's times to where you're just going to have to explain it and not show a calculation. It's very simple for them to predict it based on just the algebraic sign. So you need to be familiar with just the concept of the equation and what that means for delta G given your conditions. So some little mental math here. The best combo, something exothermic, more disorder, it's always spontaneous. And that means at any temperature. Because if this increases or decreases, and remember this is Kelvin, which means it's always a positive number, a negative minus a negative, always negative. Worst combo, endothermic, a decrease in entropy, it's never going to be spontaneous at any temperature. A positive minus a negative value, another positive, is going to be positive plus a positive, always positive. So double negative, never good. These are going to be conditional. Endothermic with an increase in randomness is going to be negative at a high temperature. Positive value minus a positive value that's going to increase with an increase in temperature will eventually become negative. Likewise, the other way, also variable. Exothermic, great. Less entropy means that this is going to be a positive value. So a negative plus a positive at lower temperatures is going to be spontaneous. At higher temperatures, then this positive value is going to overcome the negative, making delta G positive. So this mental math always makes it feel scrambled, especially on the pressure of a test. You can memorize it, best, fastest, write out the equation, walk through it each time. I do that because I'm trying to make sure it's correct, but I'm not doing a time test. You might have a mnemonic. If you find yourself just really getting stuck, go the slower route. These are questions you really shouldn't miss because they're not that complicated. You just don't want to be confused, okay? Take your time, take a breath, and move forward. A good little summary of it, again, always going to happen, never going to happen, conditional, okay? But if you have the equation in front of you, that's probably the simplest route to just think and look at what's going to happen to this value, and we want to have this being negative in order to be spontaneous. Again, other ways to think of it that you can see is this. I find this more confusing to myself, but you might find this more handy. So normal calculation, you can see these are standard. This is going to be the basis of what we have it. You're going to see the not standard when we have things that are different involving equilibrium and later on with electrochemical cells. So you're going to see a variation of Hess's law as well. Again, delta G's, you're solving the same type of math we did for Hess's law and enthalpy. You have the same idea that we did delta G before with delta H. All the values will be provided, whether it's delta H, S, G. Not likely they would give you non-standard values, but if they did, you would treat them the same. They're not going to give you mixed values. They're not going to give you standard in some and not standard in others. So no need to be feeling like they're trying to trick you or fool you in any ways. But again, remember it's products minus reactants. All right, and delta G in its standard state is 0 because it's in its normal energy state. Now, free energy and pressure, enthalpy is not pressure dependent, entropy is, because remember, if you have a larger volume, then you're going to have larger entropy. So a larger volume is always more entropy than a smaller volume, which in turn is a lower pressure is always more entropy than a higher pressure. Again, I don't expect them to have calculations based off of these, but this is a great follow-up question to a Gibbs free energy on a free response of talking about what would be expected to occur in these things to happen. You know, and a good example of these could be simply put as, for example, combustion, right? When we think of combustion, we have oxygen and a hydrocarbon together in order to have a concentration high enough in order to burn/explode. Well, if those are very spread out, right, in a room, like you turn on a little bit of gas and you have oxygen, and they're very spread out, 2 grams of methane, 2 grams of oxygen, but they're spread out across the entire room, you light a match, nothing, right? There's the energy there, but it's so spread out, the entropy is so huge, it's not going to occur, even though it's a negative exothermic reaction. However, if we compress that down, super tiny, and put all that together, then the entropy is much less, and therefore that change in entropy is not going to be as different, and so you're going to have a combustion reaction. So again, kind of following up as a follow-up question, you might have this change occur. Remember, large volume equals lower pressure. Looking at some standard calculations, your H is given, your S is given, calculate delta G. Equally put, depending on what kind of unit you might have, they might give you delta G, they might give you H, they might give you S. What's the temperature? Any one of those variables you can solve for. So in this case, you're plugging in your values. You have to be careful about watching your units. So they sometimes will give you joules. It's probably simplest to turn this to kilojoules, which of course moves your decimal over 3 spaces, and making sure that your units are in kilojoules per mole. So make sure you convert before you use them. They don't usually match. Sometimes they will. You always need to watch your units for those things going forward. And remember, your temperature is in Kelvin, not in Celsius. Different type of example. Well, I guess let's see, looking at the same type of example. Again, in any kind of AP test, they could have you solve for any one of these 3. Again, Kelvin, make sure that's in kilojoules. So when you do the subtraction, you can see that this is not thermodynamically favorable at 25 degrees Celsius. All right, and that'll leave us out to where we're at. Let me know when you come in with questions, and talk to you later. Take care.